Good morning, everyone. My name is Paul Aldana.
And my name is Jolan Santiago.
And we're going to talk about the postage tech. For today, we're going to talk about how we came about the logo, how we designed our processor, and overview of the baseline design, and some of our enhancements, and our future plans, and we're going to have time for some question and answer later on. Postage tech. Why postage? Because postage, for our register file, we always clock in new information on the positive edge of the clock. So, as you can see, new information is italicized. You can think about that like new technology, new information, and the positive edge of the clock as the future. And this is also inspired by Professor Allison from last semester, spring semester. 301, yeah. And think positive is a slogan, because even though we're having a really hard time doing this project, we always think positive and always have a positive outlook. Okay, processor design. We designed it using Verilog, as everyone did. It's a hardware descriptive language. It's a RISC processor. So, with that being said, memory access is limited to load and storing. And we have a hardware architecture, which consists of two separate memories for instruction and data memories. And since our memory only have a 32-bit word space, 32-bit space, we store the word in little endian format. So the low address gets the low word, and the high address gets the high word. For our processor, we have an average CPI of 4.446. For all these cycles, the three cycle overhead are included. So this one is pretty much a one cycle instruction, two cycle, and so on. So we have 84 total instructions, 4 more than the baseline of 80. And Jolan is going to talk about the
Alright, for our instruction types, we have operand-based instructions, triple, double, and single. Triple includes addition, subtraction, divide, multiply, and so on. For the double, we have copy, exchange, they're the same. Copy, exchange, store, load, so on. And for the single, we have increment, decrement, shift right, shift left. For the floating point instructions, we have floating point add, divide, subtract. For the conditional and unconditional jumps, we have jump and carry, jump not carry, jump overflow, or jump not overflow. And for the unconditional jumps, we have just jump. And then for the flag processor instructions, we have set carry, clear carry, set parity. Oh, that's for our enhancements. Clear parity, so on. For the immediate operand instructions, we have load immediate or high, and so on. For our instruction format, for the triple, before I get started, all the opcode is from 24 to 31, so I don't want to repeat myself. For the triple operand, we have 0 to 4 as our destination register. We have 8 to 12 as our source 2, 16 to 20 as our source 1. For our double operand instruction, we have our destination register as 0 to 4, and our source 1 is 16 to 20. For our single, we have source 1 as 20 to 16. For the jumps, we have the 8-bit, the 24-bit immediate operand value as 0 to 23. And for the flags, we have no register sets, because we don't want the user to implement or change the status flags. For the immediate operands, we have the 8-bit immediate value from 8 to 15. We have the destination register from 0 to 4, and we have source 1 from 16 to 20. For our machine register sets, we have 64 registers in total, 32 registers, which are 64 bits wide, are for the integer. We have 32 registers for the floating point instructions. We have a 12-bit status flag register. We have a 32-bit memory address register. We have a 32-bit instruction pointer. We have a 32-bit stack pointer. And we also have other 32-bit registers in the VIU. For the flag registers, it's 12 bits, as I mentioned before. 6 bits are from the floating point. We have the greater than, equal, less than, or equal, equal. And we have 1 bit for the interrupt, 1 bit for the carry, negative, 0, and overflow. Should go over here. We have I for interrupt. It sets the interrupt if there was a request, and it clears it after the interrupt is completed. We have parity. It sets if there's an even number of 1s in the register, and 0 if there's an odd number of 1s. For carry, it's set if operation generates a carry or a borrow from the most significant bit of the results. For negative, we check the most significant bit to see if it's a negative. A 1 means negative, and a 0 means positive. For 0, we just check if the result is equal to 0. And for overflow, if the result is too large or too big of a positive number or too small of a negative number, then we set the overflow flag. Alright, for the floating point register or flags, we have the not equal. If source 1 and source 2 are not equal, the flag is triggered. If it's equal, if source 1 and source 2 are equal, then the equal flag is set. If source 1 and source 2 is equal, or source 1 is less than or equal to source 2, then the less than or equal flag is set. If source 1 is less than source 2, then this less than flag is set. If source 1 is greater or equal to source 2, then the greater than or equal flag is set. And if source 1 is just greater than source 2, then the greater than flag is set. Alright, for the stack pointer, we have a 32-bit register. We start at 3FF, but we don't really write into it because we have a decrement before push. So whatever we write in 3FB. It's 3FE, I mean. For pop, we have an increment after, so yeah. Alright, and Paul will go over the thing. Alright.
So this is our top module. Pretty much our CPU contains a CU and a CPU EU. And we have the hardware architecture. We have data memory and the instruction memory separated. And we have the I/O module right here. As you can see, the I/O module and the data memory module shares the same bus. But for the I/O module, it's outputting interrupt and receiving the interrupt acknowledged from the CPU EU. The CU. You can see there's a lot of data going from CU to the CPU EU. We have our flag register is contained in the control unit itself, so we're passing the flags from the CPU EU to the CU. Then we have the buses going to the respective memory over here, and the data address. For the floating point, it stays the same. We didn't touch it. We could have touched it, made some enhancement or feature modifications. And for the integer data flag, as you can see, we could have just expanded the other mux to 3 inputs. But we didn't have time to really optimize that one. is our BIU. Okay. Now we'll talk about the muxes. For these two muxes, we expanded it to receive 4 inputs. So 0 for both muxes receives the feed data from the data memory, and for 1 we get the instruction data from the instruction memory. For 2, these are either for load I or high. And for this one, we did it differently. This is for the exchange instruction. We did this because we don't want to add another register, because that could cost money. And so we just get it from the register, going through here, and just saving the. So pretty much this are temporary registers.
Yeah, it's just a temp register.
Yeah. So we don't have to add another one. This one for the right buff, we use zeros for the ALU out and 1 for right buff 1, just to pad the when we're saving the IP to the stack. We just pad it with zeros since we're only getting the lower 32 bits from the IP.
So you actually wrote 64 bits on like a call? You'd actually write
Yeah.
0?
We put zeros first, and then we put.
Okay.
No, IP first, then zero.
Oh yeah.
Then
You have to.
And for this one, the IP mux, we have 0. We're getting it from read buff 0, and we're popping back the IP, and we're not getting back the 0 padding. And for 1, it's the reset. Oh, I mean, this is for the interrupt vector. And 2, the reg out. We want to jump to a register. And for 3, if we want to jump relative or call relatives. Now, Jolan's going to talk about the enhancement.
For our enhancements, we didn't really have time to modify the CPU. We just added a parity flag. So basically, we implemented this in the bottom of the ALU. So we have a counter, or integer I and a counter. We had a for loop that basically goes inside all the bits inside of the register. So we have Y register, and it checks if the content is 1. If the content is 1, then the counter increments, or else the counter stays counting. At the end, once the loop is done, we do a modulo 2. Basically what that does is, if it's an even number, then we shouldn't have a remainder. If it's an odd number, then we should have a remainder, and it'll set it won't set the parity flag. For the parity flag, we also included 4 new instructions. The first one is set parity. Basically, it sets the parity flag. Our opcode is all zeros, and then our name is set p. The instruction format is the same as set flag and processor. We have the RTL over here. Parity equals 1 bit, and then we have an example set p. It's supposed to be set p typo, and then the before and after. We have clear parity, basically the opposite of set parity. Our opcode is all zeros except for the last bit, it's 1. Same instruction format as the flag and processor. We have a RTL over here, parity equals 0, and then we have the example over here, before and after. We also have a jump to parity. Our opcode is 000010. We have the same format as jumps, so we get the 24-bit value, we sign extend it, and we add it to the current IP. our RTL is right here. If P equals 1, we jump. Example is right here. PC change. We also have jump if not parity. Our opcode is 0000011. Same binary format as the jumps. Our RTL is if parity equals 0, then jump. Our example is right here. The PC changes. Alright, so we tested it out here. So basically how we have it set up, it won't jump if our parity isn't set. So first we load register 14 with 0A, 0A. Then we set what was supposed to be set parity. And then jump if parity plus 1, so it wouldn't execute the halt. And then next we override register 14 with 5050. And then the results would be this. And then next we have clear carry. And then clear parity. The next instruction would be jump and not parity. This wouldn't execute if parity was set. And then the next instruction was register 15, or load register 15 with 0F. And then the last instruction is off. And then as you can see the results, we have the F for the final instruction, and we loaded register 14 with 5050, and the last 4 bits are 080. For our future enhancements, we plan to add more logic. That includes like the NOR, NAND, like rotate right, rotate left. We plan to implement the floating point flags, add jumps to that. That could have been easily done, but we just didn't have time. We also plan to add a barrel shifter, which then Eli did. We also plan to add a vector data type. This spikes graphics. It allows for usage of graphics stuff. And that's it for our presentation. If you guys have any questions.
Does anybody know how they might have done the parity generation easier?
With the XOR on every single bit.
Yeah, I think you could have just done a combo XOR.
Okay.
Yeah, that would make it.
So I'm still uncertain. So if you're setting the parity bit, does that set the parity bit to 1, you said? Or
Yeah,
instead
we set it
of,
to 1.
versus when is the parity set? Is it set every fetch?
It sets every time
automatically?
we perform an ALU operation, like add, subtract.
Okay. So, and it checks the results,
That
not
checks the results.
just the result of the ALU operation.
Now, setting the parity in the ALU, would this be for input-output, like serial communication? Or
Yeah, for UART. If you're planning to implement a UART, but we just didn't have time. You don't want to put it for future enhancements, because,
I'm doing 460, right?
Yeah. More questions?
Good. You guys did a good job. Coordinated.